Hello students, welcome to lecture 32 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture is on carpet cloaking and transformation optics metamaterials. So here is the lecture outline. We'll briefly discuss about carpet cloaking. We'll introduce this topic along with some theory and discuss some applications. And then we will look into the designing of transformation optics based metamaterials, like how you can produce artificial anisotropy in metamaterials using transformation optics. We will discuss some application specific design and how to realize those designs. So, transformation optics, we have seen that it can be used to design a cloak of invisibility. If you remember the previous lecture, we have seen that how one particular sphere can be completely hidden, okay, by routing the light rays around it. Okay. So, here is an illustration of real life invisibility cloak. There is a lady standing here, but then the tree at the back of the lady is also visible. So, this actually makes the lady invisible, right. So, to put it forward, the only way to achieve actual transparency would be if the electromagnetic waves coming from the behind the object could somehow still arrive, okay, with the same trajectory in the front of the object as though the electromagnetic waves were transmitted directly through the object. So, that is the way you can achieve invisibility. So, the object, though it is there, if it is able to pass all the waves that is coming behind the object to the front of the object, okay, whatever manipulation you do around the object, that is a different matter, okay, but then the rays will look like as if there is no object present. So, this is how you can do realize invisibility. In essence, the cloak makes its contents appear to be very small and hence negligible. So, this is the way it has been designed. So, here you can actually think of an object which is put inside a square shaped AMM target layer. AMM is anisotropic metamaterial. So, this is another way of hiding an object by reshaping it. So, when you actually look into this object, it appears to be a square shape once. So, how does it help in invisibility? Say you are looking for a circular shape object, okay, but you are actually able to hide your circular shape object inside this square shape layer, and then in the detection system the person who will be looking at this will say, okay, this is not my object that I am looking for, because I am looking for a circular object and this is a square object. So, this also is a form of invisibility. You are making your circular object invisible to some extent, right. So, this is a way of reshaping the scattering cross section of the object, or you can say radar cross section of the object. So, there are three distinct topological possibilities for cloaking. The first one is the cloaked object can be crushed to a point or to a line, and in the process of crushing the object, okay, the object will become infinitely conducting. However, this is not a problem as the objects are of negligible size. Okay, so, for negligible size this is fine and it can be rendered invisible, but it will require extreme and singular values as well as being anisotropic. It means the requirement in this kind of cases would be something like you will have anisotropic permittivity and permeability, and they may have singular values like 0 or infinity, which is very difficult to or almost impossible to realize. And the third possibility would be to crush the object to a sheet, and in that case the sheet is highly visible, and only way it can be made invisible if it sits on a conducting sheet so that this particular one is not distinguishable. Okay. So, you can understand that this is more limited in its application, but the invisibility here can be rendered without extreme values and with isotropic materials. So, this looks like a possibility to do it in real life, because here you do not actually require those extreme values of permittivity and permeability, and you can use isotropic materials to realize this kind of a sheet. Okay. So, this kind of cloaking is called carpet cloaking. Okay. So, here a cloak can help you mimic a flat ground plane. Okay. So, we understood that the carpet cloak does not require singular values for the material parameters. Thus, the range of permittivity and permeability will be much smaller in the case of a complete cloak. Okay. And you can see here that this is the object you are trying to hide, that is a ground plane, and then you are trying to put a cloak over this object, so that it is indistinguishable from the overall thing is just like this virtual system. Okay. So, the signature from this object will not be coming out. Okay. It will behave as if there is a just a plane, ground plane, okay, nothing else. So, that is how you will be able to hide the object or conceal the object. So, here this shaded region, as I discussed, they reveal the ground planes, and the observer will perceive the physical system as the virtual one with a flat ground plane, because you have put the cloak on it. So, this cloak is called carpet cloak, and this is doing the wonder. Okay. Now, let us consider the system as a 2D wave problem with electric E polarization. So, here you are able to see in the physical system, this is the coordinate x and y, okay, and in the virtual system, okay, we are considering zeta and eta, and this is the width and this is the height of the cloak, okay, in the virtual system. Okay. So, a ground plane here is basically a highly reflective metal surface which can be regarded as a perfect conductor. Now, let us assume that this is the object we are going to hide, and this is lying on the ground plane. Okay. So, you are basically covering it, and once you cover it, it should behave like the overall thing should give you a feel as if it is just a flat ground plane, there is nothing on top of the ground plane. Okay. This is how you will be able to conceal the object that is shown in the figure. Now, let us assume that the cloak is basically a rectangular size cloak which has got a width of w and height of h, just that the bottom inner boundary is basically curved upwards like this to leave some space for the object. Okay. And the whole configuration, this particular configuration in A is called the physical system, and it has got a coordinate of xy, or you can say x1 x2 if you want to use the indexed notations. On the other hand, if you look at B, that shows the virtual configuration, and this is what the observer should see. Okay. So, the coordinates there can be leveled as zeta and eta, or you can simply say take zeta 1, zeta 2, okay, whatever notation you want to follow. Now, in general, we will now consider a coordinate transformation which maps a rectangle, this particular rectangle, okay, in the virtual system to an arbitrary region, okay, like this in the physical system. So, we have to find out the Jacobian matrix, that is A of ij, that will be nothing but dou xi over dou zeta j. Okay. And here you can take zeta 1, zeta 2, or you can take zeta eta. It is better to go for this zeta 1, zeta 2 notation. Okay. They are the basis vector of the virtual coordinates which are appearing in the physical system. Okay. From that you can also obtain what is a covariant matrix, that is given by G. Okay. G is nothing but this Jacobian matrix transpose multiplied by the Jacobian matrix, that is A transpose A. Okay. So, what happens in this case? So, for cloaking, the observer perceives the physical system as an isotropic homogeneous medium of permittivity epsilon ref, that can be any value, and mu ref is basically 1. So, this is the whole thing. Okay. So, here you are basically keeping your permittivity to be 1 and your this one, the permeability to be 1, and permittivity can be anything, and that makes the system more realizable, because you are able to change the values of permittivity easily as compared to permeability in metamaterials also. So, the corresponding physical system induced by the coordinate transformation will be given by this. Okay. So, this epsilon is basically epsilon ref over determinant, square root determinant of the covariant matrix G, and you can also obtain what is the permeability mu ij, that will be given by A transpose over square root of determinant of G. With that, you will be able to write down what is the transverse and longitudinal values of the permeability. Okay. So, these will be the principal values for the permeability tensor in the physical system. So, once you know this, you can find out what is the refractive indices. They will also be like NT and NL. Okay. So, T is the transverse one and L is the longitudinal one. Okay. And you can find out it to be NT equals square root of mu L epsilon, and NL is basically square root of mu T epsilon. Okay. So, these are for the two local plane waves that are traveling along the two principal axes. Okay. Now, to indicate the extent of anisotropy in the physical system, the anisotropy factor, okay, that is alpha, okay, it can be defined as maximum of this ratio NT over NL or NL over NT. Okay. So, whichever is the maximum, that defines alpha, and that actually gives you the anisotropy ratio. So, we understood, we have got all these things for our carpet cloaking. We first got the Jacobian matrix, then we have the covariant matrix. We also find out the anisotropy factor, and you can prove that that alpha plus 1 over alpha is basically trace of the covariant matrix divided by the determinant, square root of the determinant of G. Trace is basically the summation of the diagonal elements of this matrix. Okay. And this is assumed that mu L and mu T will be 1. So, on the other hand, an averaged refractive index N is defined relative to the reference medium, that can be defined as N equals square root of NL NT over epsilon ref. Okay. So, that can give you, when you square it up, you will get epsilon over epsilon ref, and that is basically square root 1 over determinant of G. Okay. So, what we understood, that instead of using epsilon and mu ij for describing the physical medium, you can use alpha and n, which have got like geometrical meanings in terms of the matrix. So, if there is a fine rectangular grid in the virtual domain with tiny cell walls which are of size say delta by delta, each tiny square can be transformed into a parallelogram in the physical system, which will have two sides, which is zeta 1 delta and zeta 2 delta. So, that way you will be able to map this one. Okay. So, the virtual system will be able to cater to the physical system, which is like this. Okay. So, a small anisotropy will mean that a smaller value of this ratio, okay, trace of G over square root of determinant of G, while a smaller area of the transformed cell. So, the cell area is basically square root of determinant G into delta square, okay, and that will mean a larger refractive index N. Okay. So, in cloaking, the compression of space in the physical domain essentially make the cloak anisotropic that we have seen in the previous lecture. However, here when you use this kind of transformation, the approach here is to minimize the induced anisotropy by choosing a suitable coordinate system. So, if the anisotropy is small enough, we can simply drop it, and dropping anisotropy means you just make alpha equal 1, okay, and you can keep the refractive index n. In other words, you can say the physical system becomes just like a dielectric profile unit that is described with just epsilon, where you consider permeability, that is mu, to be just 1. So, that makes life more simple. Okay. So, the dielectric profile will be like this, n square equals epsilon over epsilon reference, okay, and that is given by square root of 1 by determinant of g. So, this way you are able to do it. So, this is the transformation. Okay. So, first from this is a proper you can think of rectangular grid. From that you have to go to this particular system, and you have to see how you can now define the grids. So, there are two types of grid system possible. One is called transfinite grid. Okay. So, here the transfinite interpolation is basically used, and the number of grids considered is 40 by 15, and as you can see, the grid is just a linear compression along the y direction. Okay. And the other type of, so what happens here, you can see from the color coding that the permittivity value, so n square is basically epsilon, okay, or you can say n square is epsilon over epsilon ref, that is same thing, conveying the same meaning here. So, you can see that it has got low epsilon, so that this medium will be poorly approximated as isotropic, okay. Whereas, you can use another type of mapping, and that map turns out to be the optimal one, which is generated based on modified Leo functional. So, you can use this kind of a function to generate another mapping, and that particular mapping is called quasi conformal mapping. Okay. So, what happens here in this particular grid, all the grid lines are basically orthogonal. Okay. So, how it helps? The aspect ratio of each cell, or you can say the anisotropy factor alpha, becomes a constant, okay, and the value will be around 1.042, while your n square is ranging from 0.68 to 1.96. Okay. So, anisotropy remains same in this case. Okay. So, here you can say that n or epsilon can remain finite without approaching either 0 or infinity. So, you are able to avoid the extreme values, right, and this is the result of crushing the object to a plane instead of a line, and that is why no singular points are occurring in this kind of coordinate system. And here you can see are able to use high permittivity. So, this medium is well approximated as isotropic. Okay. So, this is the final test of this particular carpet cloak. Okay. So, to test the effectiveness of the design carpet cloak, okay, you can think of the cloak to be say 4 micron by 1.5 micron. So, these are the simulation results which are shown, okay, and the cloak is defined relative to silica, which has got a reference epsilon. So, you can say epsilon reference is 2.25, okay, and then quasi conformal grid are being applied, and anisotropy can be avoided by only keeping the epsilon profile with unit permeability. Okay. So, mu is always kept as 1. So, in this case you can see the cloak varies, the permittivity of the cloak varies from say 1.5 to 4.4, and this range is pretty much doable range, because these values are close to which we can easily realize. And how you can make, you can actually take dielectric substrate and drill sub-wavelength holes of different sizes in, say, in the z direction of a silicon substrate, and that can give you this kind of values of permittivity according to the direction that you want. So, it actually makes it possible to realize. And outside the cloak, okay, so outside the cloak you can outside the cloak, so this is the cloak region, okay. So, as you can see, this is the cloaking region, this is the object, okay, and outside the cloak it is again silica as the background material, okay, and you can assume that this inner surface of the cloak, the dent that you see here is basically coated by a highly reflective material. So, to the observer, when you see, so this is with the cloak, so you can see the light is falling and simply it is reflecting as if it is a plain metallic surface, okay. But if you do not use the cloak here, that is this dotted black, sorry, the dashed black rectangle, that is basically the cloak. So, if you do not do that, you will be able to see this different scattering, and that will give the signature, give out the presence of the object. So, this is how you can actually use it. So, using this kind of situation, you can route light at your own will in the optical integrated circuits. So, here the electric field pattern is shown for Gaussian beam that is launched at 45 degree towards the ground plane, okay. The width of the beam was considered to be 4 micron and the wavelength was 750 nanometer. The background, as I mentioned, was silica, and this is where the cloak is not present. So, you can see multiple reflection that actually tells you about the presence of the object, okay. So, this is the cloaked object, it looks like as if it is just a ground plane, and this is the scattering from the object without the cloak. Here it reveals that there is something present, okay. So, we can look into some interesting applications of carpet cloaking. The first one is reshaping the scattering of objects, as I mentioned, that you can actually think of the object to be perceived. So, here it is a scattering from an elliptical object, okay, it looks like this, okay, and this shows the equivalent problem via an isotropic metamaterial layer, which actually gives scattering from a rectangular object embedded in a anisotropic medium, okay, designed by transformational optics to scatter like an elliptical object. So, this is the actual reflection, or you can say scattering happening from elliptical object, and here you have actually put this rectangular object in a anisotropic medium to give you the similar kind of scattering features like an elliptical object. So, you are basically reshaping the objects. The other one can be this one. So, another application is that here the electric field contours in finite element simulation shows reshaping of a square perfect electric conductor object into a dielectric object, okay. So, here again, so the dielectric object, okay, you have used a square PEC object, but that gives you the same look, or you can say the same scattering signature of a dielectric object. So, this is how you can actually reshape, okay. So, now we understood that carpet cloaking, though the application becomes limited, but it is more realizable, because you can think of permeability to be always 1. So, you can deal with all non-magnetic materials, and then the permittivity values are also very realistic, because you are able to avoid the extreme singular values like 0, infinity, very small or very large. Those things are very difficult to realize in real life. So, here you will see some methods of producing artificial anisotropy in metamaterials using transformation optics. Okay. So, we have discussed about sub-wavelength gratings, and we know that sub-wavelength gratings are artificially made anisotropic media. The reason is this, that when the electric field of the incident light is parallel to the slab, the grating slab, okay, they will have a different permittivity as compared to this one. Okay. Here the electric field is basically parallel to the grating vector. The grating vector will be this way, okay, and this is the incident beam, and this is how the grating will be, slab air, slab air. So, it is basically parallel to the grating vector. So, that will give you H mode or TM mode, and when it is perpendicular to the grating vector, you can say it will give you the E mode or TE mode. So, when you see, you will find out that this particular mode has got a higher permittivity as compared to the H mode. Okay. So, you can actually using this concept, you can think of extending these structures. So, they can be either, you take this kind of cylindrical rods and place them in a square lattice, or you can take a slab, okay, and then drill cylindrical holes in a square lattice. So, that will give you this particular case. Now, how do you say these are anisotropy? Because here you can see that when you take this particular material, okay, so along this axis, okay, it will actually find this kind of a scenario where you have dielectric material and air. Okay. Similarly, along this axis also here, it will find dielectric material and air interface. So, electric field will be basically like this. Okay. Whereas, in the third direction, along the length of the cylinder or rods, you will see that electric field is basically parallel here. So, that will give you high permittivity. Now, if you think of the birefringence, this will be called positive birefringence, because this you can call as extraordinary permittivity, and these are the ordinary ones. So, this is epsilon E minus epsilon O. So, delta epsilon here is basically positive, and it has been seen that this gives you smaller delta E, whereas if you drill holes, you will actually get larger delta epsilon. Okay. It is not E epsilon. Okay. You can also think of negative birefringence that you can achieve by placing sheets of different material periodically. So, say you have epsilon 1 and epsilon 2, two different materials, and they are alternating. Okay. In that case, along the material you have high permittivity along both x and y, but this is a grating. Along the grating you will have low permittivity. Okay. So, this will now your extraordinary one. So, epsilon E will be smaller than the ordinary permittivity, right. So, why we bother about all this? Because when we discussed about the applications of transformation optics in the previous lecture, we saw that we require this kind of anisotropic materials. Something like, we will just take an example, say you want to stretch this particular coordinate system, okay, and that will help you move the objects apart. Okay. But then this stretching in reality should be accomplished by replacing the right hand side, this particular colored half, with a new kind of material, so that the rays actually remain in this particular slope. So, this was thoroughly discussed in the last lecture, so I will not go into the details of it again. Okay. So, here we have seen that this is basically the step 1 that actually tells us about generating the modified coordinate system, and this is the calculation of the equivalent metamaterial properties that causes the rays to change slope in a desired way. Second would be to define the modified coordinate system. So, suppose that the objective here is to stretch the x3, this positive x3 side, okay, by a factor of s. So, in that case we have seen the transfer or modified coordinate system will be x1 prime, which is same as x1, x2 prime will be same as x2, but x3 prime will be same as x3 over s. Okay. So, this is how we have done also in the previous lecture. We have seen that the goal is to end in a standard uniform Cartesian coordinate system, and the stretching property should be now incorporated in the material. So, for this, start with a stretched coordinate system like this, okay, and then you think that the coordinate system must compress in space, and that should help us obtain the equivalent permeability and equivalent permittivity of that particular stretched space, something like this. So, this will be the new material which will have this equivalent permeability and permittivity. So, we have seen the calculation of Jacobian matrix. So, if this is the new coordinate system, you can find out the Jacobian matrix, and it is basically 1 0 0 0 1 0 and 0 0 1 over s. So, this is what we require, and once we have the Jacobian matrix, you can calculate the permeability, the equivalent permeability using this formula, that is A transpose mu naught A over determinant of A, and doing this particular maths you can find out that it comes out to be S mu 0 0 0 S mu 0 0 0 mu over S. Okay. Similarly, the same thing will also apply for the permittivity, okay, and you can obtain the permittivity values to be this one. So, it is S epsilon 0 0 0 S epsilon 0 0 0 epsilon over S. So, with this particular values you have now able to get that kind of bending. Okay. So, that was the whole idea, that you can stretch your actual coordinate system to space out two different materials or antennas in a particular chip, and that particular property of stretching of the axis can be now put into a new type of material. So, you do not need to physically change the length of the space, but you can change the material, so that equivalently that particular stretching effect is taken into consideration. Now, mu E and epsilon E, these are the equivalent permeability and permittivity, and looking at the tensors you can understand that the two elements are same and third one is different. So, these are basically uniaxial, and when S is greater than 1, okay, that is your stretching it, okay, you can see that the third one will be smaller than the other two. So, extraordinary one will be smaller than the ordinary one. So, this we can name as negative uniaxial crystal, okay, or metamaterial. So, that is how NUM, negative uniaxial metamaterial, the term has come. Now, again the question comes back to us, that how do we actually realize negative uniaxial metamaterials? Now, for permittivity it is bit easy if you remember this particular cheat sheet, that when you have this is the slab, and if you have electric field parallel to the slab, okay, you will have high permittivity, but when you have something normal to the surface of the dielectric material, it is low permittivity. Okay. Using this you can actually think of designing negative uniaxial metamaterial, okay, and we have seen that new negative uniaxial metamaterial basically comprise of alternating layers of dielectric, so like epsilon 1 epsilon 2 repeated. This is the period capital lambda, and the fraction of one material is f. So, you can say the length of one layer is f lambda, the other one will be 1 minus f lambda. Okay. So, this is the equivalent material permittivity that you want to realize. So, you have epsilon O, that is S epsilon, and epsilon E, the extraordinary one, is basically epsilon over S. And from this you can also find out what is your S stretch factor, that is basically square root of epsilon O over epsilon E, and epsilon is nothing but square root of ordinary epsilon and extraordinary epsilon. Okay. Now, where this is important, coming back again, that you can use this kind of negative uniaxial metamaterial to implement the stretching factor. Okay. Say you have two antennas on a chip which are very closely spaced, but ideally you want that space to be, say, the distance to be, say, 10 times or 100 times more, but you are not able to do that because of the limitation of the chip size. In that case, you can actually put a negative uniaxial metamaterial that will implement this stretching within that small gap. So, equivalently, okay, you will be able to say physically the antennas will be located where they are, but then they will feel, the waves will feel that as if they are far away from each other. Okay. So, this is what we are trying to achieve. So, S epsilon 0 0 0 S epsilon 0 0 0 epsilon over S. So, you can see that it is high along two axes and small along one axis. Okay. And these are the parameters that you have already discussed. So, you can actually put this alternating layers of two material, and that can give you this particular negative uniaxial metamaterial. Now, for negative uniaxial metamaterial, you can, if you have smaller contrast between epsilon 1 and epsilon 2, your effective values also will be small, and here you can see extraordinary is always, the red one is extraordinary, that is always smaller than the epsilon naught, and this is the fill factor where you can get the maximum anisotropy. Okay. And if you consider larger contrast between epsilon 1 and epsilon 2, then you will be able to achieve higher, delta, that thing also, anisotropy, and at larger fill fraction. So, this F is basically the fill factor at which maximum anisotropy is achieved, and in both cases you can see this is negative uniaxials, that is why epsilon E is much smaller than your epsilon O. So, this is what we will be able to achieve if we use this. Now, what we understood, that epsilon O can go to the maximum value and epsilon E can actually get the minimum value. From this graph you can understand, okay, that the maximum value can be achieved by this one and the minimum value by the epsilon E. Okay. And you can also find out the fill fraction. Okay. So, these are the limiting values that you can achieve using different fill factors. Okay. So, this is the relationship between the epsilon mean and epsilon max with the fill factor, and epsilon 1 and epsilon 2, which are the permittivity of the two different layer material that you are using. And you can also get the maximum anisotropy strength using this formula, that is basically your epsilon max minus epsilon mean. So, with that you can optimize and find out the value of the fill factor that will give you the maximum anisotropy, and that turns out to be this. And when you have that particular fill factor, you can also find out what is that anisotropy that you are able to achieve. The same thing you can also repeat for positive uniaxial material. So, positive uniaxial material is basically array of blocks, they can be cylindrical or square cross section, does not matter. So, these are basically rods or blocks, you can say. Here again, for this is for smaller dielectric constant between contrast between epsilon 1 and epsilon 2. So, here the effective values are also a bit low, but when you go for larger contrast, you can go up to very high values of effective permittivity. And here you can see epsilon E is larger than epsilon O in all the cases, because it is a positive uniaxial material. But how to realize? You can realize using this kind of structure, and negative uniaxial you can realize using those layered this one, layers of alternating layers of different or two different materials. Okay. Now, if you carry this forward, this anisotropy material, the positive anisotropy material, there are different structures that you can think of. So, the gray one shows the material, the white one shows air. So, this is basically a cylindrical rod you can think of, and this is a cylindrical hole. This is a square hole, square rod, this is a square hole. Okay, so these will repeat in square lattice, whereas you can similarly have this one. This is basically a cylindrical rod in hexagonal lattice. This is a hexagonal rod in hexagonal lattice. These are the inverse structures where you have white portion as the air, okay, air holes. So, why these different structures are seen? You have to understand that what kind of range of values you are able to achieve using this kind of things. So, it has been found that hexagonal shaped rods are difficult to manufacture. So, the circular ones are basically easy to manufacture, okay, and they can give you higher anisotropy as well. So, and the rods, as you see here in theory, they can be like freestanding, but when you fabricate this, there have to be small connectors, okay, connectors between the rods to hold the structure together. Okay. So, you can actually think of a material for this kind of structure, okay, or the entire thing can be just made of polycarbonate, which has got a permittivity of 2.57, and then you can think of optimizing the thickness of the support rod and what should be the radius of the dielectric rod, so that you can get the highest anisotropy. So, you can see the thickness should be as low as possible and the radius should be around 0.4 r by a, should be 0.4, that will give you the highest anisotropy of almost 0.2. These are the simulated values. So, okay, I will go to this one directly. So, you can also see that the uniaxial symmetry gives you the highest anisotropy, and based on these results, so these are the different parameters. As you can see here, this is the radius of this cylindrical rod, this is the height of the rod, okay, this is the thickness T of the connector, and this is the lattice period A. Okay, these are the different parameters which are being used, and we have seen that the radius is around 42% of the lattice constant, and that corresponds to this one. So, it is actually 0.42 where you have got maximum anisotropy. So, r by a is the lattice constant, is 0.42. So, you can say the radius is 42% of the lattice constant. Okay. And you also see that the radius persists to be constant irrespective of the dielectric constant being used. Okay. And these are the fabricated ones. So, here you can see these are the cylindrical rods that you see, okay, and these are the connectors. Okay. So, these are made in 3 different orientation. Okay. So, these are the parameters that have been used. A, lattice period is 8 millimeter, radius is 6.4 millimeter, height is 13.86 millimeter, and this is the thickness. Okay. And this is how it has been used. So, if you take rods, in one case the rods are, these are the rods, okay, you see the rods, cylindrical rods. So, the rods are in y direction, in y direction, sorry, first you have done in x direction, then in y, and then in z, okay, 3 different cases, and then using a VNA you have measured the dielectric constant, and you have seen that along 2 direction they are similar, and along the 3rd direction, that is the z direction, you see it is different. So, it actually gives you that anisotropy. Okay. So, it actually shows that using this kind of concept you are able to make metamaterials which are uniaxial metamaterials. Okay. So, this one was an example of positive uniaxial metamaterial, but for those stretching application we will require negative uniaxial metamaterial, but this paper shows fabricated result which has been published. That is why from this group, and that is why I am showing you the result of this positive uniaxial metamaterials, and this should motivate you that yes, this kind of structures can be realized, and all these things that you have discussed in this course till now, they are all achievable. So, with that I will stop here, and in the next lecture I will cover the introduction to alternative materials for all these different applications like plasmonics, transformation optics, and so on. So, any queries, you can drop an email to this address mentioning MOOC in the subject line. Thank you.